Awesome. Good turnout today. So thanks everyone for coming. I just wanted to give everyone a quick overview of some upcoming events in the new year. So this will be our last event of the year. My name is Ibrahim. I'm the current chair of the VGS. And so in January we'll have our joint lecture with EERI. We'll have Dr. Dashti speaking. That'll be on January 20th. And then on the 29th, we'll have our annual joint lecture with TAC, the Tunneling Association of Canada. So we're still just determining the lecturer there, but just keep an eye out on your inbox and you'll hear from us very soon. So those are two upcoming events. And one other note. We have finalized our date and location for the symposium for next year. That'll be on June 5th, and it will be held at the Paradox Hotel. So that'll be a new venue for us. So I'd like to bring up Omar to introduce the speakers. Thank you.
Hello, everyone. Good evening. My name is Omar. I'm one of the program directors for the VGS, and I'd like to welcome you to the second annual VGS Legacy Lecture, a foundational force in geotechnical earthquake engineering, the legacy of a true pioneer. Each year, this series recognizes leaders who have shaped our profession here in BC, and tonight we are honored to celebrate the extraordinary legacy of Dr. Finn. For over 5 decades, Dr. Finn's pioneering work has helped define modern geotechnical engineering. Unfortunately, he could not attend this evening, but he has asked us to express his gratitude and appreciation towards the VGS community. Tonight's lecture will be delivered by 2 of Dr. Finn's former colleagues, Dr. Thavaraj, Senior Geotechnical Engineer and Principal at Klohn, Crippen, Berger, and Dr. Jason Dowling, Senior Structural Engineer and Principal at Associated Engineering. Both will share reflections not only on Dr. Finn's technical legacy, but also on their personal experiences working with him. So please join me in welcoming Thava and Jason as we honor the remarkable career and enduring impact of Dr. Finn. Thanks.
Good evening, everyone. It's a great honor for me to deliver this lecture. I was Dr. Finn's last Ph.D. student to pursue research in geotechnical earthquake engineering. That's probably the reason I am delivering this lecture today. Omar already said that he couldn't be here due to some mobility issue, but we will share some of these what happened today with him through some photos and other things. With that one, I want to start this, and most of you know Dr. Finn, and you don't need any introduction. And I want to start with a personal tribute to Dr. Finn. He was a friend and a mentor like no other. I met Dr. Finn as a graduate student at UBC. I was new to Canada at the time, and I heard that he was top in his field, and I was unsure what to expect. So I went to meet him, and at the time he was sitting with Miss Kelly Lamb, another fine lady, and dictating a technical paper. When he saw me, he recognized me, he stood up, gave a big smile, shook hands, and cracked a joke that immediately put me at ease. And most of you who work with him know that if you meet him once, you will think that he is your friend. And I have never seen him being sad or worried, and always full of energy. And he was a mentor who taught from first principles, always starting with the fundamentals. And he didn't teach us formulas and how to think and understand the why, and solving problems by applying the basic mechanics and the common sense, which is very important for the geotechnical engineering. And that's the skill I developed and I owe to him. And he gave his gift of knowledge to me, and not only that one, he gave his personal books also, which was a good gesture I cannot forget. And he attended my graduation with his wife, and it was a deeply meaningful moment for me. He's a rare blend of brilliance, humility, and humanity. You are in trouble. Finn is finger tracking the alphabet to the kid who was going to defend his Ph.D. thesis. And he's supporting him to stand on his own. And he's introducing the kid to the world, this time to a Japanese colleague who wanted to get some deformation analysis done for Hokkaido dikes. And he gave his books to the kid because this kid never owned a book before and relied on the library throughout his entire grad program. And Dr. Finn is congratulating the graduating kid. And he attended this kid's graduation with his wife, very kind and very caring, Miss Tomris. And Finn lied for the first time ever. Apparently the kid has learned the alphabet. He's a global authority in geotechnical earthquake engineering. And for 50 years, his contribution to geotechnical earthquake engineering were nothing short of groundbreaking. A career that earned respect and inspired admiration across all continents. He spent a considerable amount of time in Japan, where he commanded a very good respect. He was recognized not just for his research, but for shaping the profession for the future generation. His awards, honors, high-impact publications, more than 350 of them, are too numerous to mention. He left no area untouched to make his unmatched mark. Ground motion, site response, liquefaction, constitutive model, numerical models, and laboratory testing. And he went beyond academia to help owners, consultants, and agencies to solve some tough and emerging problems, including the U.S. Army Corps of Engineers. He worked closely with them in their assessment of their dams and the rehabilitations. He is a true pioneer and a global authority in geotechnical earthquake engineering. He laid the foundation for the UBC's Geotechnical Earthquake Engineering program and transformed it to one of the top programs in the world with the help of his colleagues he mentored or hired, late Professor Byrne, late Professor Campanella, and Dr. Wade. They were giants in their own field, numerical modeling laboratory and the institute testing. And he led the group to the prominence in those three areas, which were pillars in geotechnical engineering. And he collaborated with giants in the field to elevate UBC in the world stage. He worked with Professor Harrison, Professor Kenji Ishihara, and many others. And even at the time, he fostered a cross-disciplinary collaboration, recognizing the importance of the structural and the seismological integration. He worked with many structural engineers and many seismologists even at the time. And his relentless pursuit of excellence created a lasting culture that continues to inspire even today. The legacy he built at UBC continues to uphold UBC's global reputation in geotechnical earthquake engineering, and UBC is recognized worldwide because of that. And he had a global network of influence. He trained generations of engineers and researchers across the globe. He consulted on major infrastructure projects involving hydro, water dams, tailings dam, bridges, port structures, from Soviet Georgia to Mississippi. He influenced seismic codes and guidelines in multiple countries. His students now teach courses, lead research programs, conduct workshops, develop design codes and guidelines, and design and build critical infrastructure. He probably taught every geotechnical engineer in BC until 2000 and many beyond. His legacy lives on not just in papers, but in the people he taught, trained, groomed, and influenced. Let's look at Dr. Finn's journey from 1954 to 2000. He completed his bachelor's degree in University of Ireland in 1954, then flew to Washington State to complete his master's and Ph.D. in University of Washington. And he joined UBC in 1961 as a professor, and his initial research interest was in classical plasticity theory, not in the geotechnical earthquake engineering. And that one actually laid a strong foundation for his future models, because if you want to do work in the constitutive model, you had to have a very good background in classical plasticity theory. And in 1964, he went to UC Berkeley as a visiting professor. And then in March 1964, the M9.2 Alaska earthquake occurred, and you can see in this slide the damage to the $1 Million Bridge and highway and the slide. And then in June in the same year, the M7.5 Niigata earthquake occurred, and you can see the damage to the Showa Bridge and the apartment buildings. You would have seen these pictures in many other places. And these two earthquakes showed the power of the liquefaction, because the liquefaction dominated the damage. And it highlighted the need to understand the liquefaction better and its consequences. So at the UC Berkeley, Professor Harris Seed with his students, Professor Idris and Lee, they led the research on the liquefaction. Idris is an analyst and Lee is an experimentalist. And Dr. Finn, while being with them, he firsthand witnessed how difficult or what the challenges are in the liquefaction research. It is struggled to duplicate a slide failure, and Lee struggled to simulate a liquefaction in the triaxial test. So he shifted his focus from plasticity theory to liquefaction. It was a critical need at the time. So he returned in 1966 to UBC, and he acquired funding and commenced his research in liquefaction, and he established a soil dynamics laboratory with a shake table. And in 1966-67, Dr. Finn published a paper on the static and seismic analysis of a dam using a finite element. And this publication showed the power of and the potential of the finite element method at the time, even with the limitation in the memory and the computing power compared to what we have today. And that actually led him to go to Soviet Union to work there for a few months, analyzing a very large rock-filled dam which was going to be built in Georgia. In the meantime, from 1964 to 71, at UC Berkeley, Harris Seed and his colleagues continued their work, and they developed these programs. You all are familiar with that one, this shake, quad 4, and flush. Shake is for the one-dimensional site response analysis, and quad 4 is for a two-dimensional finite analysis embankment with a variable damping, which was a nice feature in the one at the time, and flush is for a soil structure interaction analysis. But all these programs used a total stress-based equal and linear model, but soil exhibits a nonlinear historic behavior and also develop water pressure. And at California Berkeley, they also continued their research simulating liquefaction in cyclic triaxial and simple shear. And they developed their first liquefaction chart by relating the pore pressure ratio with the relative density, and subsequently much later here in the mid 80s they developed their first liquefaction chart using the seed simplified method by relating the cyclic resistance to SPT N160, and this was the predecessor for the current liquefaction chart. Then came the 1971 San Fernando M6.6 earthquake, and this earthquake occurred about 11 kilometers from the San Fernando Dam, which is located about 30 kilometers north of the Los Angeles. And this lower San Fernando Dam experienced a severe damage. The pre-earthquake freeboard of about 11 meters reduced to only 1.5 meters that prevented the dam breach. The upper San Fernando Dam also experienced some displacements in the order of 1 to 2 meters. And in this one, you can see on the right-hand side the configuration before and the after the failure, because the significant movement caused a drop of freeboard from 10 meter to 1.5 meter. And this earthquake, this 1971 earthquake, it exposed the weakness in the total stress-based equivalent linear models. Dr. Finn recognized the need for an effective stress nonlinear model because soil exhibits nonlinear historic behavior and develop pore water pressure, and because of the development of the pore water pressure, the effective stress reduces. When the effective stress reduces, stiffness strength reduces, that causes the liquefaction. So in 1975, Dr. Finn made a landmark contribution to liquefaction with the development of his model called Martin Finn seed model, or MFS model. This model can predict the pore water pressure during shaking or cyclic loading. And in the figure on the right shows, the bottommost figure shows this cyclic loading, and the figure in the middle shows the shear strain development, and the figure in the top shows the development of excess pore water pressure due to that cyclic loading, the gradual increase and the triggering of the liquefaction. At that point, the effective stress is reduced to almost zero. And this was undeniably a significant breakthrough in capturing the mechanics of liquefaction and the dynamic response. And this was missed in all total stress-based equivalent linear model. And let's look at this MFS model. This first equation shows the relationship between the incremental volumetric strain, which is expressed as a function of the shear strain amplitude, and the accumulated volumetric strain, which is basically expressing the shear volume coupling, which was captured in this equation with the 4 coefficients from C1 to C4. And the corresponding pore water pressure can be expressed as a function of that volumetric strain with the rebound modulus. So it's a very simple model, but elegant, and it could capture this pore water pressure generation during the cyclic loading, which was important in dynamic behavior of the soils. And the figure here on the left hand side, it shows the volumetric, the relationship between the pore water pressure ratio and the volumetric strain, and the figure on the right shows the number of cycles and the pore water pressure ratio. So between 1975 and 1980, Dr. Finn spent time in implementing his MSF's model in computer programs that actually changed the practice at the time. The first one was the DayStar 2, which was developed in 1975. It can do both total and effective stress analysis, the site response analysis. And in this DayStar 2, a hyperbolic stress strain model was used, and the Masing criterion was used for the unloading and the reloading part. And Dr. Finn extended this Masing criterion to capture the irregular cyclic loading typical of earthquake. And this figure shows a typical output from the day strap, starting from the top input motion, shear stress time history, shear strain time history, and the pore pressure. And you can see that this particular program can capture the increase in pore water pressure and the liquefaction triggering. And the figure on the right shows the stress strain loops during that earthquake loading, and you can see it is not an equal and linear model, it is a nonlinear hysteretic model. And in 1982 he developed this TARA 2. The TARA 1 was a total stress program, and the TARA 2 is the effective stress program. And in 1986 he enhanced that TARA 2 to come up with that TARA 3 with some extended capabilities. And this, when we develop this program and the model, it needs to be calibrated using the element test like a cyclic simple shear or triaxial, or some full-scale test or centrifuge test. And this particular program was validated using some test results, centrifuge test results from the University of Cambridge. And in 1988, he developed this program called TARA 3FL. This is to capture the post-liquefaction, large deformation, large strain response of the embankment dam. And in that one, he used a very simple model, but that model, he incorporated the post-liquefaction residual strength to capture the post-liquefaction deformation using the large strain formulation, the Lagrangian formulation. Even now, we struggle to capture this large deformation or large strain, but Dr. Finn laid the foundation even in 1988. And Dr. Finn's, TARA the model is, available in FLAC. And he worked closely with the U.S. Army Corps of Engineers and for the performance assessment of their dams, and also for the retrofit or rehabilitation. And here on the left hand side you can see this Sardis dam, which was retrofitted by driving some concrete piles, and in the middle you can see the Mormon Island Auxiliary Dam in California. And also he simulated the damage experienced by the Upper San Fernando Dam. And he also used these programs to predict the damage experienced by the dikes in Hokkaido, Japan. And he developed a very simple correlation to predict the settlement using only the geometrical parameters, the height of the dike, the thickness of the non-liquefiable layer, and the thickness of the liquefiable layer. And the right hand side bottom, you can see a correlations between the crust settlement and the non-dimensional parameter, and it shows actually some blind prediction, and it worked well for that particular scenario and for that particular case. So it was a kind of a simple one, and you do a fancy analysis, more elaborate analysis, finally reduce to come up with something simple. You can use it for your screening level analysis. And from 1990 onwards, his interest changed to soil structure interaction, piles, retaining walls, basement walls, and buildings in general. And Jason is going to cover some of them in the subsequent lecture today. And he also contributed, or he was an active member of that BC seismic retrofit of school building project. I believe that Jason is also going to talk about that one too. So let's look at this Dr. Finn's contributions. This is a typical embankment dam with some liquefiable layers, strain softening sills, and with some ground improvement. And the input ground motions are important because we represent the earthquake loading with the input ground motions, and Dr. Finn has some contributions on that one, on the laboratory test and the liquefaction triggering evaluation, and a constitutive model to capture the pore water pressure response and at its consequence on the soil behavior, and the amplification effect through one-dimensional site response analysis and two-dimensional finite element analysis to capture the response of these earth structures, and the performance-based design we use now. So you can see that he didn't leave out any subfields of this geotechnical earthquake engineering. He made his mark in all these fields, and this particular figure shows, he contributed to all of them, and we can look at them one by one now quickly. And the boundary condition is very important for a model analysis, and he did some work using both rigid and transmitting boundaries, because rigid boundaries are not a real one where the waves reflect back into the system. The transmitting is more real, and he introduced his transmitting boundaries even in the 70s in the DESRA program. And for the site response and the ground motion amplifications, I already mentioned that he developed this program DESRA, which can do both total and effective stress analysis, and the model is a nonlinear hysteretic model, and he provided these site amplification factors for the 2005 NBCC. He recognized the impact of the topography and the effect of the basin effect due to deep sedimentary basins even at the time, and he published some papers on that one. On the liquefaction evaluation side, we typically use the stress-based liquefaction chart. The figure on the left-hand side, which was developed as a part of the 1997 NCER workshop by a group of experts, and Dr. Finn was one of the members of that one, and this chart was developed as a part of that workshop relating the cyclic resistance ratio with SPT, and there's a chart for CPT also. And in the 1980s, he developed a method using the strain, not stress. The figure in the middle shows the relationship between the pore water pressure ratio and the length of the strain path. So it's a strain-based assessment of the liquefaction as opposed to stress. And in the 1980s, he also developed a program called ProLig to do a probabilistic-based liquefaction. Even nowadays, we still use the deterministic-based liquefaction assessment, but in 1975, he developed this program. At the time, the cyclic triaxial and cyclic simple shear testing were done under undrained conditions. The difference between undrained and drained, as you know, that in drained condition we keep the valves open and let the water drain. In undrained, we close them. When we close them, Dr. Finn recognized that there is an issue with the system compliance, including the membrane penetration. So he wanted to overcome that one, so he developed or he modified the UBC simple shear apparatus to do the constant volume cyclic testing. Following the constant volume apparatus, which was developed in NGI or Norwegian Geotechnical Institute by Berger in the 60s. So he used that one to modify this UBC apparatus to do constant volume testing instead of the undrained testing. And in the constant volume testing, the valves are left open, but the volume is kept constant. So during shearing, the soil grains undergo rearrangement, and that rearrangement causes the reduction in the vertical stress, and the reduction in vertical stress is taken as the pore water pressure. The pore water pressure is never measured in constant volume test, an elegant concept actually. And this figure shows this UBC NGI type simple shear apparatus. And Dr. Finn demonstrated that in terms of the effective stresses, the behavior of the dry and saturated samples are identical in constant volume test. Again, a kind of a beautiful concept. The figure on the right shows the relationship between the void ratio and the number of cycles to liquefaction. So the curve shows the cyclic resistance, and the open symbol shows the dry samples, and the closed symbol shows the saturated samples. And you can see this both lie on the same curve, showing the behavior of the dry sample and saturated sample of sand in constant volume is the same. And he made contribution. I already covered some of them already in my previous slide. Seismic performance evaluation involving liquefaction, the liquefaction triggering, and his MFS model to capture the water pressure, and the implementation of Thava in these programs, the 1D TESRA and 2D Tara 3 and 2D Tara 3 FL, and the validation of some of these using this tri-exam simple shear and centrifuge test. He also published several papers summarizing the case histories. So like I mentioned at the beginning of this one, he didn't leave any subfields of the geotechnical engineering. He made his mark on ground motions, laboratory tests, liquefaction triggering, constitutive model, 1D site response, 2D performance evaluation, and the performance-based design. Finally, some reflections on Dr. Finn. His passion for the field and the work is truly admirable. His relentless pursuit for simple but elegant solution to the tough problem is remarkable. Usually, one good thing or the key thing about these famous professors are they will do a very high-end numerical analysis and very rigorous calculations, but when they publish or present them, they will convert them into a very small one, a kind of a regular practicing engineer can understand and use it. That's the beautiful about those things. So Dr. Finn also, if you read his papers, you will find that it is very easy to understand all these different or sometimes complex concepts. His career shines with the brilliance, with the global impact that shaped the discipline. His contributions continue to guide our practice and research. He trained generations of engineers and researchers around the globe. He is more than a scholar. He is a mentor, leader, and a friend to many. His legacy lives on through direct and indirect influence in every theory we teach, every model we use, every test we run, every structure we design, and to withstand earthquakes. And his impact is woven into the very fabric of our work in one way or the another. His legacy shaped the geotechnical earthquake engineering. Thank you, Dr. Finn. Your legacy continues to inspire all of us. We wish you health and happiness. Finally, acknowledgement to Dr. Finn's former students and colleagues, University of British Columbia and Vancouver Geotechnical Society for organizing this legacy lecture, and finally the KCB. Thank you for your attention.
Thanks, Thava. So Thava did the heavy lifting there on summarizing Dr. Finn's career. I'll try and fill in some little pieces around the edges. I worked with Dr. Finn for 4 years as a postdoc at UBC. I met him first in 2012 on a Zoom call with Carlos Ventura. It was a job interview. I got on a plane 2 months later and moved to Vancouver, and I started to work with him and met him in person for the first time. My first impressions have held up since. They are of someone with a very warm heart,
phenomenal intellect and some old school charm. I spoke to him yesterday on the phone, and he wanted me to pass on his gratitude, so I'll say that again. He appreciates what VGS are doing here this evening and is sorry he couldn't make it. He is humbled and appreciates the event, so thank you very much. I also wish he could be here to talk about his work himself. He will do a much better job of it than I can. So I included a picture of him talking at the start, so you could imagine him describing his work instead of me. Thava talked about his list of accolades. They are truly impressive. Read in their entirety, it seems quite ridiculous and unreal, the stuff he managed to do. What stands out most, though, is the breadth of the experience and the disparate fields, societies, countries that presented him with these honours. It really is a very broad church. It's not surprising to me, though, and I'm sure it's not that surprising to Thava as we worked with him, but it is very surprising. So I'll try and share a little bit of that with some stories. He was educated in Ireland and the US, so his education is not Canadian, but he moved to Canada, set up the first geotechnical earthquake engineering school in Canada, in UBC, and worked for 6 years in Japan. So quite an international reputation there. His international reputation includes teaching and practice invitations, again in different countries across Europe, Russia, Japan, China, and the US. So Thava said 350 papers. I think the number is closer to 400, which is an incredible number of journal articles. And what I find most impressive about that is they're actually in 50, at least 50, I stopped counting, 50 different titles of journal. So that's 50 different journals in different specialty fields. So quite a broad range of contributions. He was also editor of the International Journal of Soil Dynamics and Earthquake Engineering, which I know we all probably tried to get into. On faculty since 1961, he mentored over more than 40 Ph.D. students, which is an incredible legacy. The list of honorary memberships and medals is also ridiculous. It includes the Harry or the HB Seed Medal in 2014. And we forget, though, that he was actually a contemporary of Harry Seed. So Seed's name is huge in geotechnical earthquake engineering. He was a contemporary. He originally worked on plasticity, again, as Thava pointed out. But the 1964 Niigata and Prince William Sound earthquakes, and then an personal invitation by Harry Seed to Berkeley, shifted his perspective and his career. He paid strict attention to the work that Seed and Idris and Lee, again Thava mentioned the names, were doing when he was in California. In particular, when Ken Lee had been trying to get a soil sample to liquefy in the lab, but hadn't quite managed it yet. And one night something went wrong with the pulsating load apparatus. Instead of pulsating, something grabbed the head of a sample, and instead of pulsating, lifting up and then unloading, it pulled it up and down, turning it into a kind of impromptu cyclic load test, and the sand liquefied. The simplified method of cyclic stress ratios caused by earthquake shaking followed pretty shortly thereafter. I've put it on the slide there for you. It's amazing to think that he was around and kind of literally in the room when this groundbreaking and fundamental equation was being born. Site response is another method that he got involved in, and he got heavily involved in due course. He came back from Berkeley determined to get into soil dynamics and liquefaction. At the time, another problem was presenting itself. You couldn't get samples to test in the laboratory. If you tried to sample a sand that was potentially liquefiable, it densified. And so you couldn't test the sample as it was in the field. Databases were studied, and that was one way around this, but there was another specialty birthed at the time, and that was to study the material in the lab. His research group set up the first centrifuge in North America with motion control dedicated to geotechnical research. He was instrumental in bringing research into UBC. Most professors at the time were dedicated teaching professors, and he started hiring research professors. He developed, this is from a magazine, the UBC magazine, a picture of him and a student, Japanese student of his. He developed an infamous hiring process after he was given carte blanche to travel. He would bring candidates out to dinner, and knowing that personality of the candidates was very important, he would check how they behaved after a few glasses of wine. While he was Dean of Applied Sciences, which he was for 8 years, I think, a student of his was visiting a well-known professor in Germany. At a seminar, the student asked a group of German professors if they knew UBC. German professors replied, no, they didn't. The German professors asked the student to name a few UBC professors. He went through some names. They didn't recognize any, but when he mentioned Dr. Liam Finn, they all recognized the name. They did not recognize UBC, but they recognized Dr. Liam Finn. When people thought of UBC Applied Sciences, they thought of Liam Finn. Thava spoke about the pioneering work on effective stress analysis, finite element modeling, constitutive modeling, the Martin-Finn seed model, path-dependent calibration processes. 1975 represented a unique time when the state of the art and the state of practice were the same. Shake and Quad 4 was very influential programs. But from 1975 onwards to about 2000, when Thava graduated, the young boy graduated, Dr. Finn went on to refine all these processes, including the complexities and nonlinearities in models such as these, the Versat, Tara, Desra, I won't mention them again. He moved much faster than practice, and the gap started to broaden as Dr. Finn and his students continued in their work. They started to use the tools that he and they developed together to analyze and study soil structure interaction and to draw some interesting conclusions. They developed very fast finite element programs that could be used to study different soils and structures and how they interacted. They showed that the common practice of evaluating pile foundation response and using pile cap motions as inputs into the models of structures such as bridges can seriously underestimate the displacements and inertial forces. In such cases, coupled analysis or soil structure interaction is necessary. The effect of stronger levels of shaking is to widen the gap between the loads carried between the interior and exterior piles. These are some of the figures he and his co-workers generated. He found interesting results as part of this work for certain frequency intervals in the loading, the dynamic loading. The piles closer to the center actually take a larger portion of the load and the large dynamic amplification factors expected for these piles in the center. The effect of the stronger shaking is to widen this gap between the loads carried by the interior and exterior piles on the whole, and the results hold for longer bench-shaped bridge piers, such as this one. He noticed two results not previously reported. The difference between pinned head and piled head condition is quite pronounced here. The other striking difference is that the case of 2x2 or 3x3 pile groups, the group factor actually increases, and the groups provide more resistance than the sum of their individual contributions, indicating the smaller piles in pile cap exerts a disproportionately large influence. Dr. Finn was instrumental in that BC Schools project, again, that Thava mentioned. I'm sure quite a lot of people in the room have worked on it. I know some of you for sure have. It involves analysing and retrofitting the BC schools. I think it's around 800 or so. The estimated cost is in the billions. UBC were engaged by the Ministry of Education to conduct geotechnical and structural research into retrofitting the schools to come up with efficient, cost-effective solutions. They set up a technical review board to ensure the retrofit guidelines were followed, and Dr. Finn was a big part of that process for a very long time. His work was involved in many different streams of research as part of that project. This starting with site characterization, site response analysis, lateral spreading, and soil structure interaction. He's developed simplified but rigorous methods of evaluating liquefaction potential and lateral spreading based on other work at the time. He updated them for probabilistic ground motions, which were used in the project. with such a large inventory, the team had to prioritize cost effectiveness. So site characterization was, of course, part of the work, but because of the large number of sites, they looked at ambient vibration, which was a lot cheaper than other invasive methods. So the figure on the left shows the blue band with the step line in the middle, the average results and standard deviation from ambient vibration results. The system takes dispersion data that they developed together, runs Monte Carlo simulations to output the mean and standard deviation. In the same figure, the solid circles are SCPT data points, and hollow represent, I think, downhole data for comparison. So the results were within 5 or 10% and at a fraction of the cost. The figure on the right shows a similar study comparing where the yellow dots are ambient vibration results. Site response analyses were conducted as part of that work too. Empirical shear wave velocity depth relations and site data were used to generate large data sets incorporating uncertainty. Monte Carlo simulations again used to vary site parameters and determine the response at the surface, considering very little data. Dr. Finn led the team in developing early versions of the liquefaction guidelines, which are used as part of that project. The torch is probably passed to someone in the room. The document provided liquefaction advice, liquefaction factor of safety, settlement, lateral spreading. He proposed methods of estimating displacements based on Yode's method, which I'll cover on the next slide. The document provided commentary on liquefaction drift limits as they relate to components of drift in liquefaction, so the residual drift, the horizontal demand, and the vertical settlement demand. He proposed methods of estimating lateral spreading. This is based on Yode's method I mentioned. We have the equation there, Yode's equation. The method includes the chart for site class D for a different for different magnitudes. It provides the average acceleration as a function of distance from, I think, 3 attenuation laws. It was in Yode's paper. The question is, what do you do with probabilistic ground motions? He proposed 2 methods of dealing with this. The first was using the deaggregation from Natural Resources Canada, which gives bins of magnitude distance pairs and their contribution to the hazard. So the figure on the bottom left, you calculate how each of these pairs contribute to that acceleration demand, and then you sum them up. So adding horizontally takes care of the contribution for each magnitude. Adding the column gives the total displacement. So using probabilistic demands now. The second way of doing it is to use a hazard program directly. And if you were in UBC, you know Dr. Finn taught 504, which was using probabilistic seismic hazard analysis tools. The work is done by calculating hazard acceleration with an epsilon of 0, so no variation about the mean. These 2 methods, in Vancouver, the average epsilon might be 2, for example, so 2 standard deviations above the mean. So these 2 methods give similar results. That's what's in the bottom right, and it's compared to another result where you use the full acceleration at the site. Dr. Finn spoke many languages, including Russian, as Thava mentioned. He spoke it so well, in fact, he could pass for a social sciences professor. He lived in Russia for a while after being invited to give some lectures there and work on that dam that Thava mentioned. A local radio station once booked him for a telephone interview, taking the call at the scheduled time, and he started chatting away to the host in Russian. He was a bit surprised by the social sciences question. He was expecting earthquakes or geotechnical types questions, but towards the end, he realized that the interviewer had actually confused him with a social scientist professor and booked the wrong person. He winged it, and so the interviewer could save face, and they were quite happy with his answers. He was fluent enough to speak on Russian radio in a field that wasn't his. He could also speak Japanese. He traveled to Japan with the Canadian delegation after the 1985 Kobe earthquake. This is Carlos Ventura and Liam Finn in the picture at a park. One day after work, he and Carlos and Peter Byrne wanted to go sightseeing into this park where the emperor used to live back in the days when they still had emperors. The park was closed, but he spoke to the park attendants in Japanese, describing them as visiting earthquake experts, and the workers let them in and gave them a personal tour of the park. He returned there when he retired from UBC at 65, and became the first Anabuki chair of Foundation Geodynamics at Kagawa University, and he stayed there for 6 years. He is still very well known in Japan. It is not surprising that he's so skilled a linguist, as he grew up actually speaking 2 languages, Irish and English. His fluency in Irish helped him when he had a go in the field of bridge construction. This inauspicious looking bridge, single-span bridge taken from Google Maps, is actually the first post-tensioned bridge deck structure in Ireland. The bridge was originally constructed for the railway in the 1840s with cast iron girders on stone abutments. During summer vacation between years at university, young Liam was a site engineer for the rehabilitation project of the OB 56 Dublin to Cork Sallins Line Bridge, where the cast iron beams were replaced with post-tensioned concrete deck slabs. This was the first bridge of its kind in Ireland, and Liam was there to oversee its construction as a student. On the first day of construction, fresh-faced young Liam rocks up to the site, clean work boots, introduces himself to the work crew. The crew clearly don't think very much of him, and they just carry on speaking Irish amongst themselves, thinking that this was just some posh bridge engineer, academic type, and he would be a pushover and let them do whatever they wanted. They generally start making a slow start on the work. He listens to them chatter. They're starting to make fun of him, and he lets them talk for a while, but then he joins in the chat and starts giving them back better than what they gave him. After that, he added the extra reminder that he signs their time cards, and they very quickly started putting in very hard-working shifts. And this is now still exists. The bridge is still standing today. He was also not afraid to get stuck in the field. This is a video, which see if I can press it here. A video taken at Painter Street Overpass. Anyone who studied earthworks might know it. It's a very well-known, very highly instrumented bridge. And this is Dr. Finn at the back and Dr. Carlos Ventura in the front. They're doing a microarray test, so they're hammering a steel plate to send out an impulse, and there's an array of sensors that will pick up the impulse. And they are not afraid to add weight to the plate so that it doesn't move around. He has a great sense of humor and makes stressful days much easier. Despite the incredible intellect, he remains infinitely approachable and warm. He's responsible for where I am now. He's responsible for so many other people probably in this room. And for many of us who are lucky to get to know him and into his orbit, we feel grateful and proud to have worked with him and to call him a friend. I hope I haven't done too bad a job of sharing a little of his immense character. Thank you very much. I'd like to acknowledge these people too, of course. Liam and his wife, Thomas, and Carlos Ventura for some of the slides here, and everyone else. So, thank you.
Thank you, Jason. Thank you, Thava. That was truly remarkable. It's great seeing, what went into some of the methods we're using today, and wow, what a life. So again, thank you on his behalf, and on behalf of the VGS, we had some gifts for both of you, and one for Dr. Finn, which we'll find a way to drop off along with some photos of the event. And I've also wanted to mention that Thava generously offered to provide a donation, a $1,500 donation in honor of Dr. Finn to support the VGS and our contributions to education and sponsoring a student or another VGS member in attending the CGS conference. So thank you, Thava. We really appreciate it.